We have become so reliant on radio signals bouncing off the upper atmosphere and beaming down from satellites that the ionosphere has become a critical part of our technology. From aircraft communications and radar to managing navigation of the world's shipping lanes and global positioning for fishing trawlers to locate their catch. GPS for the military, on the ground and in the air. Yet we know very little about this region of Earth's atmosphere. Critically, there are times when global positioning signals become unreliable. The satellite and radio signals twinkle in much the same way as bright stars appear to do at optical wavelengths. Irregularities in the ionosphere, referred to as ionospheric depletions or bubbles, span the hemispheres at the equator and are a major element of the low-latitude geospace region.
It's very important for us to understand the ionized portion of the atmosphere, the ionosphere, as well as the upper atmosphere, because that's where satellites are, low Earth orbiting satellites are orbiting in that region. Astronauts are exploring that region, as well as the communication and navigation signals travel through that region. And so when you have disruptions in the ionosphere and variability in the ionosphere, that can affect our navigation and communication systems.
The ionosphere lies some 40 to 600 miles above Earth's surface. The upper atmosphere and ionosphere change constantly in response to forces from above and below, including explosions on the Sun, intense upper atmosphere winds, and dynamic electric field changes. These irregularities form huge horseshoe arcs between hemispheres, with their apices centered on the magnetic equator. To learn more, NASA conducted a mission called CINDY, the Coupled Ion Neutral Dynamics Investigation. CINDY was designed to measure ionization of the upper atmosphere, including the behavior of the irregularities responsible for the GPS twinkling, which turned out to be quite surprising. The ionosphere becomes unstable shortly after the sun sets. As darkness falls, ionized atoms and molecules begin to recombine into a neutral state. During this transition period after sunset, irregularities are quite strong. As the night wears on, however, these irregularities were thought to fade and eventually vanish around midnight. CINDY found many irregularities around sunset, but they did not vanish around midnight. On the contrary, there was another peak in irregularities during the middle of the night. This second peak has appeared most pronounced from June through August. Scientists aren't sure yet why this second peak occurs or why it varies by season. The CINDY mission ended with the re-entry of the spacecraft into Earth's atmosphere. Researchers still had much to learn about the ionosphere and how it can affect GPS and other satellite systems. To understand the tug-of-war between Earth's atmosphere and the space environment, NASA created the ICON satellite.
So with the ICON mission, we're looking at the very upper levels of the Earth's atmosphere and the charged plasma environment that surrounds the Earth that we usually consider as the inner edge of space. So that region is called the ionosphere, and that's what gave us the name for the Ionospheric Connection Explorer. But really a lot of what is happening there is being driven by the winds and the composition of the Earth's atmosphere.
So these altitudes, the thermospheric altitudes that the ICON mission is investigating are typically too low for satellites to fly in and too high for weather balloons to get to, for example. So we need to use remote sensing techniques to get the information at the right altitudes. And the atmosphere actually helps us do it because there is something called an air glow. The atmosphere naturally just glows at those altitudes more during the day and less during the night, but it's always there. This air glow is always there. And by just looking at the color of this air glow, we can find out about the wind and the temperature, actually. So it's The atmosphere, in a way, is helping us to understand how it is behaving by sending out this air glow. And if we build the right instruments to look at particular aspects of the color of the air glow, we can get the information that we want.
So what ICON is trying to do is observe these two systems at the same time from one satellite. So it does that with 4 instruments, and broadly speaking, 3 of those are kind of camera instruments that look out at the Earth off on the horizon. One of them measures the temperature and wind of that atmosphere. One of them measures the composition of the atmosphere. One of them is getting the plasma environment, this charged particle environment. And then there's a 4th instrument that measures the charged particles and their motion and things at the location of the spacecraft.
High-altitude wind shear is thought to be one of the factors for GPS twinkle.
It's just the movement of the atmosphere, same thing as we experience as wind down here, except for the winds are generally much faster up there, and there's very little atmosphere, so the pressure is very, very low. So those are the 2 major differences between what we think of when we say the word wind here and what we experience up there, what the instrument sees up there.
ICON was placed aboard a Pegasus rocket and flown into the stratosphere under the belly of an orbital ATK aircraft. Once it is at the right altitude and heading, the rocket drops away, then ignites its main engine, carrying the spacecraft into orbit. Once in orbit, the spacecraft is commanded by scientists at Mission Operations Center at the Space Sciences Laboratory at UC Berkeley. ICON then began its study of the frontier of space, the dynamic zone where terrestrial weather from below meets space weather from above. In this region, the tenuous gases are anything but quiet, as a mix of neutral and charged particles travels through in giant winds. These winds can change on a wide variety of timescales, due to Earth's seasons, the day's heating and cooling, and incoming bursts of radiation from the Sun. To understand what drives the variability in the ionosphere is very complicated, a system that is driven by both terrestrial and space weather. A second satellite mission was needed, another suite of instruments in a higher orbit named GOLD. A first for NASA, GOLD was piggybacked on a commercial satellite.
The GOLD mission stands for Global Observations of Limb and Disk, and it's a very important mission for us to understand the upper atmosphere of the Earth, the thermosphere and ionosphere of the Earth. It is our first hosted science payload that NASA's flying on a commercial spacecraft. And so that is a new innovative way for us to do science that maximizes our private sector partnership as well.
GOLD will be sitting 22,000 miles above Earth, which means that it can see a whole half of the Earth, all of the Western Hemisphere. And it will be hovering over one particular point on Earth, watching the dynamics of the atmosphere play out below.
From geosynchronous orbit, GOLD can scan half the planet at a time.
I am excited about this mission because GOLD will be getting information about the upper atmosphere much faster than ever before, and will be able to look at effects that are more like the weather that we experience down here on Earth.
two influences on the ionosphere are space weather and weather below, closer to the ground. Space weather is the realm of the Sun, coronal mass ejections affecting our magnetic field and showering us with energetic particles. The Sun's energy starts in its core, a giant fusion engine where hydrogen atoms are turned into helium atoms. The energy produced there moves up through the convection zone to the Sun's surface, the photosphere. Moving magnetic fields contribute extra energy along the way, bursting from the surface, emitting light and heat that is channeled by the Sun's magnetic field, generating the turbulent surface, including prominences, flares, and coronal mass ejections that spread out into the solar system.
Space weather is the field that studies how what's going on the Sun affects us here on the Earth in our near space environment and on the space environment on other planets.
These powerful bursts of energy travel outward toward the planets. This space weather, consisting of light and thermal radiation, includes high-speed solar wind and energetic particles which collide into planets orbiting the Sun. Earth has some defense, its magnetic field that deflects and absorbs much of the energy, distorting the magnetic field. Some energy is captured and follows the magnetic lines to the poles, generating auroras.
NASA hopes to achieve with the Golden Icon missions a better understanding of the near-Earth space that's so important for our global infrastructure.
To help predict space weather, many Sentinel satellites watch the Sun closely. Iris is one of them. It watches our star in ultraviolet wavelengths and is able to give us warnings of extreme space weather events approaching Earth. This space weather has a direct influence on our ionosphere. Another tool to watch both the solar weather and Earth's weather together is about to go into operation, replacing its aging predecessor. GOES-R is a next-generation weather satellite with the latest in technology. It will be 5 times faster, advanced resolution cameras giving greater coverage for hurricane tracking, real-time mapping of lightning, and improved solar flare monitoring. Almost by accident, the Fermi X-ray telescope in Earth's orbit discovered another source of gamma-ray particles coming from Earth. Under just the right conditions, lightning storms fire off some of the highest energy light naturally found on Earth, terrestrial gamma-ray flashes, or TGFs. Rising and falling snow and ice particles repeatedly collide, filling the cloud with electrical charge. Once the electric field is strong enough, a current flows and a lightning flash occurs. The flash produces an abrupt reconfiguration of the electric field. In some cases, a surge of electrons rushes towards the upper part of the storm at speeds nearly as fast as light. When deflected by air molecules, these accelerated electrons give off gamma rays, producing a TGF. Data from NASA's Fermi Gamma Ray Space Telescope suggest more than 1,000 TGFs occur each day all over the globe. Tropical storms far from land tend to generate less frequent lightning. Nevertheless, observations show they are surprisingly prolific producers of TGFs. Tropical storm Manuel made landfall just shy of hurricane strength. As it rapidly weakened, it produced 2 TGFs within 24 hours. More typically, TGFs are associated with the strengthening phase of a storm. As Typhoon Bolavin rapidly developed in 2012, thunderstorms nearly 500 miles from its center launched a TGF with 4 distinct pulses. So far, the record holder for TGS is the rapidly strengthening tropical wave that later gave birth to Hurricane Julio. It produced 4 TGFs within 100 minutes. A 5th followed the next day, with nothing further. For stronger storms like hurricanes and typhoons, TGFs are more common in the outer rain bands, which host the highest lightning flash rates in these storms. The findings provide new insights into the relationship between storm intensity, lightning frequency, and TGFs. This adds another important piece to the puzzle of our understanding of TGFs and how they are created in thunderstorms, the most powerful natural particle accelerators on planet Earth.
Ultimately, the science that we learn from Golden Icon will help us be able to predict the near-Earth environment that affects our communication and navigation signals and capability, but also how space weather affects the upper atmosphere, which can translate to effects on the ground in terms of our power systems and our navigation systems down below.
The march of technology must go on. ESA and the European Union can see the future of global positioning, and it is a growing market, with more and more technology requiring their services. The Galileo program is nearing completion with a total of 26 satellites orbiting at 22,000 kilometers. The penultimate launch of 4 Galileo satellites aboard an Ariane 5 will occur soon. As with all other Galileo satellites, these newest additions will fly in a medium Earth orbit. The last launch of 4 satellites will occur in the near future. Although the constellation is not yet complete, it has been in operation for almost a year since the European Commission announced initial services on the 15th of December 2016.
The completion of the constellation will take place in the summer of 2018, where we launched the last Ariane 5 with 4 satellites, which will bring the total up to 26 satellites. So we have at that moment 2 satellites in reserve, and we will then, after that, start putting some extra reserves in space in order to be prepared just in case.
These services were the first step towards full operational capability, and a first opportunity for the Galileo system to prove its worth. Independent measurements have since shown that in terms of performance, Galileo is the best operating positioning system in the world.
On the 15th of December 2016, the Commission announced initial services. This was an important moment because this was the first time that we formally announced that there was a certain service available with a certain quality for a certain time of the day. Since then, we have been building out the constellation, and it has been improving every day. We now have independent measurements of the performance of the Galileo system, and it is actually, to be honest, and we are very proud of it, the best in class. We are having a better performance than our 3 competitors from the US, which is the well-known GPS system, the Russian GLONASS system, and the Chinese Baidu system. So, of course, in ESA we are excessively proud of this, and it is now important that we keep building on this performance and hopefully keep at the forefront of the developments.
But the work on Galileo is far from done. The European Commission and ESA are already working on the next generation of Galileo satellites and infrastructure. They aim to continuously improve the system and explore the boundaries of technological possibilities while trying to meet market demand with potential new applications or services.
The system will undergo continuous improvements. Obviously, the market is asking for that. The technology is ready for it. Every couple of years, there are new possibilities. And the combination between what the technology can offer and what the market is demanding leads then to decisions on how to improve the system so that we can provide further and more services. A number of areas, for example, which are coming is the so-called Internet of Things, which will require positioning in sensors. And these sensors have very little power and very little battery capacity, so we need special signals for that, probably. And in addition, another area which is of interest is autonomous driving, where satellite navigation is going to be a very important component, but where it needs to be integrated with all sorts of other sensors in cars in order to make sure that autonomous driving becomes a reality.
With more launches to complete the constellation and set up redundancies, Galileo's performance and availability worldwide will continue to improve gradually, keeping Galileo at the cutting edge of satellite positioning technology. Today, the only publicly owned satellite system has also proven to be the best.